Welcome back to Calculus 1. In this lecture, we're going to explore a very important topic in calculus, the relationship between derivatives and the shape of a graph. All right, you may think back to earlier in the course, we were mentioning a long-term goal, one that would take us quite a while and topics to learn how to address, which was sketching the graph of a function, was something that we would be working towards later. And as it turns out, that later is now. So once we now have our differentiation rules and some other ideas related to derivatives, absolute maximums, critical points, we can now kind of work towards this long-term goal, given a function, to sketch its graph. So we have three examples there. They're all pretty simple. And what we're going to basically ask is, for these functions, sketch the graph. Now you might be thinking, why would we need calculus to do that? We can just basically plug in x values, calculate the y value, plot that point, and repeat that. That's essentially what your graphing calculator does, but much more efficiently and quickly than we can by plugging in. Now that is a valid option, but there's really no learning of how calculus relates to the graph of a function. We're going to take a second and new option, which is seeing how the first and second derivative of a function tell us information about the graph of the function. And as it turns out, even if we're not really primarily interested in getting the graph, seeing what the first and second derivative tell us about the function, that lays the foundation for what occurs later in the calc sequence, particularly those of you moving on to multivariable calculus, Calc 3. Now this all starts to get very involved, so we're going to split this kind of very dense topic into three separate parts, three separate lectures. In this lecture and video, we're going to cover part one, what does the first derivative tell us about the function? The second part, we'll get to what does the second derivative tell us about the function, and then the third part is finally pulling all this together to sketch some graphs. Okay, so for this lecture, we're going to focus on just this question. What does the first derivative tell us about the function? And the answer, I'll spoil the surprise, is it tells us where a function is increasing or decreasing. Now, this could have been introduced shortly after we covered the mean value theorem, which is the primary reason the mean value theorem is used in calculus to kind of lead us to this, increasing and decreasing functions. But it's not really, I think, useful at the time. The mean value theorem is nice, but I find it best to wait to the introduction of the relationship to a function being increasing and decreasing, right towards where we get to being able to sketch graphs. All right, so let's go back to pre-calculus, which was probably when you last encountered increasing and decreasing functions. At the time, you would have been given the graph of the function, like we have here. Pretty simple graph. Notice both the ends of the graph go up towards infinity as you keep going to the right and left. Now, in your pre-calc course, you would have been asked, for this graph, determine the intervals of x values, that is, over which the function is increasing, and the intervals of x values over which the function is decreasing. Increasing basically means the y or function values get bigger as you go to the right. Decreasing means the y or function values get smaller as you go towards the right. All right, if we just take a look at our graph going from left to right, the first interval where our function here is increasing is for x values between -1 and 2. We write that as the open interval, -1 to 2, parentheses on both endpoints, indicating exclusion for the endpoints. Make sure you don't interpret that as the ordered pair, -1 for x, 2 for y. So we're writing these as intervals of x values. So our function here is increasing on the interval -1 to 2. And if you look also a little bit further to the right, the function is also increasing on the interval 3 to positive infinity. Similarly, if we go left to right, the y values go down, get smaller. As we go left to right, for this first interval, -infinity to -1, and notice between the local max and local min, the function is also decreasing. We're going to see that relationship between increasing, decreasing, the local max and local mins fully later in the lecture. All right, so at the time for pre-calc, this was all pretty straightforward. What we want to start to do is see how derivatives, particularly the first derivative, kind of play into this. So we want to kind of think, what is a derivative? Earlier in the course, we gave several answers, so that way, for different problems, we might have different approaches and views for how to interpret derivatives. Since we're thinking graphically here, let's recall one answer to what is a derivative. A derivative is a slope of a tangent line. Now, to see the relationship between the first derivative and increasing, decreasing, let's take a look at the intervals where this function is, let's say, increasing. And let's look at the interval -1 to 2. At any point between -1 and 2, if you were to look at the tangent line to the graph, all those tangent lines for x values between -1 and 2 have positive slope. And if you look where an interval where the function is decreasing, let's say from 2 to 3, the tangent lines between x equals 2 and x equals 3 have negative slope. And we see this relationship where the function is increasing, the tangent lines have positive slope, which basically says the derivative is positive, since derivatives represent slopes of tangent lines. And where the function is decreasing, the tangent lines have negative slope. Now, this is not a proof, but it illustrates this relationship. The mean value theorem is what lays a technically correct proof for this relationship between the first derivative and increasing and decreasing. The formal proofs are left to kind of what occurs beyond the standard calculus sequence. So we have our first test here, what sometimes is referred to as the increasing decreasing test, which is really simple. It basically says where the derivative is positive on an interval, then the function is increasing on that interval. And there's a similar result where the derivative is negative on an interval, the function is decreasing on that interval. Now, as simple as this test is to state, there's a drawback. It doesn't tell you how to find these intervals. So for instance, how given just an equation, we might find those intervals as listed above, -1 to 2, 2 to 3, or 3 to infinity. Now, how might we find these intervals? Well, let's take a look at all the endpoints of those intervals listed above. The endpoints referring to -1, 2, and 3. If you look at the graph there, at -1, there's a local min. At x equals 2, there's a local max. And at x equals 3, there is another local minimum. Now, what's special about those? -1, 2, and 3 are critical points. They're points on the graph where the derivative is 0, where the tangent line is horizontal, where it has 0 slope. And it's the critical points that we're going to focus our attention on to find these intervals. Keep in mind, the derivative being 0 is not the only way to have a critical point. There is a second way where the first derivative is undefined. That also gives critical points. So let's go ahead and take a look at a basic first example, just to get comfortable with how we would answer these questions and tie this in with the first derivative and critical points. Pretty standard example here. We're given a function, x cubed minus 27x minus 20, and we're asked to determine the intervals where this function is increasing and the intervals where it's decreasing. Now, one option is we could use the graph to answer this, but that's kind of circular. We're going to kind of use these ideas to eventually sketch the graph. All right, now we're going to split this into a few steps just to make the work manageable. The first step, as we were mentioning a few moments ago, the intervals that we're interested in are going to come from the critical points. So a first step, find the derivative. That's going to be a first step for most problems for the remainder of our Calculus 1 course. But once you have the first derivative, you use that to find the critical points. All right, again, thinking back to our intro example, the critical points, -1, 2, and 3, those were the endpoints of the intervals where the function were increasing and decreasing. We use here in step 2 the critical points to create what's called a sign chart for the first derivative. And the word sign here refers to positive or negative sign. So basically the critical points, we'll use that to get intervals, and then we'll determine on each interval if the first derivative is positive or negative. The third and final step there makes use of our increasing decreasing test. Any interval where the first derivative is positive, the function is then increasing. Any interval where the first derivative is negative, the function is decreasing. So at this point, just to get warmed up for this lecture, maybe pause the video and give yourself an attempt at finding the critical points. This one should go pretty quick. All right, now you should have found 2 critical points. Let's just check. Your derivative here only requires the power rule. Some following examples might require some differentiation rules like product, quotient, and chain rules. Here we get for our derivative 3x squared minus 27. We can factor that by first factoring out 3, and then the remaining part in parentheses x squared minus 9, that factors as a difference of squares, and we get here a complete factorization, 3 times x plus 3 times x minus 3. This expression, because it's a polynomial, is never undefined, so we find critical points just by setting this first derivative equal to 0, and we can set each factor to 0, and we should pretty easily find 2 critical points, one coming from each factor there. Our critical points here are x equals -3 and x equals +3. All right, at this point, that was all something we learned in a previous lecture. Now comes the new part, the sign chart. Now with our 2 critical points, we're going to split the x-axis into intervals. If we have 2 critical points, if we make 2 cuts in the x-axis, we get 3 intervals. Here's a nice basic framework for what a good sign chart might look like. I sketched the x-axis, and I split it at each critical point, -3 and +3. And that's kind of indicated by the vertical dashed line there. Those 2 critical points split the x-axis into 3 intervals. The intervals being -∞ to -3, the middle interval -3 to 3, and then the rightmost interval 3 to +∞. Now our goal is on each of these intervals is to determine if the first derivative is positive or negative. And to do that, we're going to pick what's called a test point in each interval. Now we could pick any x value that we want for the test points, but ideally pick small values and integers if possible. For the middle interval, -3 to 3, 0 is a good test point value to pick. So we'll choose as our test points -4 for the leftmost interval, 0 for the middle interval, and +4 for the rightmost interval. Again, you could pick any x values within those intervals, as your test points. So we could have chosen, going left to right, test points -5, +1 for the middle interval, and maybe +10 for the rightmost interval. Now, a nice little tip is if we were to plug in those test points to our unsimplified derivative, notice the unsimplified version being 3x squared minus 27, plugging in 4 and -4 could lead to a really tedious order of operations calculation. That shouldn't be difficult, but we can actually save ourselves some time by plugging these test points that we chose into the simplified expression for the first derivative. In other words, here, we're going to plug in these test points to the factored derivative 3 times x plus 3 times x minus 3. Now, this actually becomes a legitimate shortcut, a true time saver, if we don't worry so much about getting the precise y value or output value to the derivative here, but rather just determining the sign, positive or negative. So if we plug in -4, notice each set of parentheses, plugging in -4, you get a negative value inside each set of parentheses. And if we just multiply out, a negative times a negative becomes positive. What that means is our test point, -4, gives a positive value here for that derivative. So that means on that interval from where the test point occurred, -∞ to -3, our first derivative is positive. Similarly, if we plug in x equals 0 from the middle interval, that test point, to the simplified derivative, you should find you get a positive times a negative, which just simplifies to a negative. So that means on our middle interval, -3 to 3, the first derivative is negative. And then on the rightmost interval, 3 to infinity, we chose a test point, +4. Plug in x equals 4 to the simplified derivative. Both factors become positive. A positive times a positive is positive. In fact, I'm positive that it's positive. All right, now with our sign chart fully determined, we have all of our intervals, and for each interval, a corresponding sign for the first derivative. We can now make use of the increasing decreasing test. Any place there is a positive derivative, the function is increasing. Any place there's a negative first derivative, the function is decreasing. So we find here the intervals in question that we were asked to find. The function is increasing on the interval -∞ to -3, and it's increasing on the interval 3 to infinity. We combine those two intervals together with the union symbol there. All right, and then the interval where the derivative was negative gives us the function being decreasing on the interval -3 to 3. All right, so most of the work, once you find the critical points, is just taking care to create a kind of detailed sign chart. As it turns out, the sign chart, we can actually use it to answer a related question. Here we were asked to find the intervals where a function is increasing and decreasing. The sign chart, as we have it kind of described here, can also be used to answer another question. And what we're going to look at next is how basically we have a nice simple test or way to determine if a critical point is a local max or local min. Now you might be thinking, why do we need a test? There's something important I want to make sure we all understand. Not every critical point corresponds necessarily to a peak or a valley, to a local max or local min. Now there's a standard example to illustrate this, and it's for the function x cubed. Now if we were to take that function and just ask first, find the critical points, we need the derivative. The derivative is pretty simple, 3x squared. And if you set 3x squared equal to 0 to find the critical points, you do find x equals 0 as the only critical point. Now, since we know the graph here, we can see that x equals 0 on this graph, the tangent line is horizontal. Right at x equals 0, the tangent line becomes momentarily horizontal. To the left or right, the tangent line has positive slope of 0. And we see here, while there is a critical point for this function x cubed, x equals 0, the graph of x cubed has no peak or valley, no local max or local min at that critical point. All right, so with being able to find the critical points, to be able to sketch a graph, we're going to have to know for each critical point, is it a peak, a local max, or is the critical point a valley, a local min? Now we're going to kind of lead into what's called the first derivative test. Let's see this relationship. What I have sketched here are a simple local maximum and local minimum. Just a very brief, simple sketch to illustrate what the first derivative test that we're going to be getting to, what that tells us. All right, so we have our local maximum here, a peak, and a local minimum, a valley. All right, each local max and min there has a critical point, a point where the tangent line is horizontal, where the first derivative equals 0. To get this test that we call the first derivative test, we're going to look at what the first derivative tells us graphically. And again, that's something about slopes of tangent lines. Now, if we take a look at the local maximum to the left of that peak, to the left of the critical point, the tangent lines have positive slope. To the right of that peak, the right of the critical point, the tangent lines have negative slope. All right, so what that says is the derivative changes sign at that local maximum. And something similar happens to the local minimum. To the left of that critical point, the tangent lines now have negative slope. To the right of that critical point, the tangent lines have positive slope. So again here, for this local minimum, the sign of the first derivative changes. And what we see here is there's a particular change in sign for each local maximum and local minimum. A local maximum at that critical point changes sign in first derivative going from positive to negative across the local max there, the critical point. And for a local min, the first derivative changes sign from negative to positive. So as long as there's a change in the sign of the first derivative, we get either a local max or local min. The specific sign change, positive to negative or negative to positive, tells us if we have a local maximum in the positive to negative case, or a local minimum in the case of a sign change from negative to positive values. All right, and this is basically what the first derivative test says. But let's go ahead and give the precise statement, since there is kind of a third possibility. All right, now the first derivative test starts off where we have already found the critical points for a function. So our first derivative test determines if a critical point is a local max or local min. So we need the critical points first. All right, and the first two parts there are what we kind of already kind of reviewed in the little sketches that we gave a few seconds ago. If the first derivative changes from positive to negative at the critical point, positive to negative corresponds to a local maximum for that critical point. The second part, if the first derivative changes from negative to positive at that critical point, then the function has a local minimum at that critical point. Now we get a local maximum or local minimum only if there's a change in sign of the first derivative. If the first derivative does not change sign at a critical point, if it's positive on both sides or negative on both sides of the critical point, then the function has no local max or min at that critical point. And again, that's like the critical point x equals 0 for the cubic function x cubed that we looked at a few moments ago. Now, before we move on to example 2, example 3, and example 4, which I'll give everyone time to make an attempt at, let's go back to example 1 with our completed sign chart. At the time, we used our sign chart to determine the intervals where a function is increasing or decreasing. And as it turns out, this same sign chart works for our purposes now of the first derivative test. We have our signs here, but instead of just asking for where the function is increasing or decreasing, we can use our sign chart to see if there's a change in sign at any critical points. Our critical points for example 1 were -3 and +3. And if we look at our sign chart, let's first look at the critical point x equals -3. Notice on the left of -3, the first derivative is positive. On the right side of that critical point, the first derivative is negative. And if we think for the first derivative test, a change in sign of the first derivative from positive to negative, that means that critical point is a local max. And if we look at the other critical point, +3, now the change in sign of the first derivative is the other way. On the left of 3, the middle interval, the first derivative is negative, and on the right of the critical point 3, the first derivative is positive. A change in sign of the first derivative from negative to positive corresponds to a local minimum. So our sign chart kind of fulfills two roles. It tells us the intervals where a function is increasing and decreasing. And if you have your sign chart here created like I have, it actually answers the question of applying the first derivative test, determining if each critical point is a local max or local min. All right, let's go ahead and take a look at some examples where we are asked to apply the first derivative test. I'll give everyone an attempt at each of the following 3 examples, starting with example 2. This one's probably the most straightforward since we don't need any differentiation rules to find the derivative. So pause the video here and give yourself time to answer all 3 parts. They kind of lead into one another. You can kind of combine parts B and C together with your sign chart for the first derivative. Pause the video and give yourself a few minutes to make an attempt at this. Welcome back. Let's go through part A. This one should be straightforward to find the derivative, just using the power rule. You can simplify your derivative by factoring out 12x squared. And if we now set each factor to 0, setting x squared equal to 0 gives us a solution x equals 0. And then setting x minus 2 equal to 0, we get another critical point, x equals +2. So part A goes pretty quick. We have 2 critical points. This function, again, a polynomial, is never undefined, so we don't have to worry about that possibility where the derivative is undefined to give us a critical point. Here, it's only where the derivative equals 0. Now, with our critical points, we can create our sign chart, and the sign chart, we're going to use it to simultaneously answer parts B and C. So we have 2 critical points, 0 and 2. We'll split the x-axis at each of those x values, giving us 3 intervals. The intervals here are -∞ to 0, 0 to 2, and 2 to +∞. Now we can pick any test points we want, But let's just go from left to right with test points x equals -1, x equals +1 for the middle interval, and x equals 3 for the rightmost interval. If you plug those test points into the factored or simplified derivative, you don't have to worry about, for instance, cubing or squaring 3 and then dealing with order of operations. We can just worry about if each factor is positive or negative. And if you plug in these test points to the factored derivative, you should find very quickly you get for your signs in order negative, negative, and positive. And at that point, we have enough information in our sign chart to determine the intervals where the function is increasing. That's only on the interval from 2 to infinity. And the intervals where the function is decreasing, -infinity to 0 and 0 to 2. Now notice I'm including the endpoint 0 there with parentheses, because we find here with the first derivative test, the critical point, x equals 0, there is no sign change in the first derivative. It's just negative on both sides of the critical point 0. That doesn't correspond to a local max or local min. It's neither. X equals +2 is, however, a local minimum. The sign change goes from negative to positive, which corresponds from the first derivative test to x equal 2 being a local minimum. All right, let's move on to example 3, one that might require some combination of differentiation rules. All right, here you're going to have to use a combination of product and chain rules. Pause the video, and again, give yourself several minutes to make an attempt here. Welcome back. This one, hopefully you're comfortable with finding the first derivative. We use product and chain rule. And since each term contains the exponential e to the -2x, we can factor that out, getting this nice factored first derivative, 1 minus 2x times e to the -2x. Now, if we set the part in parentheses, 1 minus 2x equal to 0, the solution to that is x equals 1/2. We don't have to worry about the exponential factor equaling 0, since we already know previously when covering critical points, exponential functions never equal 0. So we get a single critical point, 1/2 here. We get a very simple sign chart. We're only splitting the x-axis at a single x value, 1/2. And if we also keep in mind exponential functions not only never equal 0, exponential functions here, like e to the -2x, the graph stays entirely above the x-axis. Here, e to the -2x is always positive. So if you plug in, let's say for our intervals, your test points x equals 0 and x equals 1, we should have a very quick way to determine the sign of the first derivative here, just by the part 1 minus 2x in parentheses. And you should find with your test point 0 that you get a positive first derivative. And with your test point 1, you get a negative first derivative. And what that tells us is the function is increasing on the interval, -infinity to +1/2. And it's decreasing on the interval +1/2 to +infinity. Since the sign chart shows a change in the sign of the first derivative, going from positive to negative, that sign change corresponds to a local maximum. All right, let's move on to our final example. Here, example 3, the differentiation rules required were product and chain rule. To round things out, you might have a guess for what we're going to look at in example 4, maybe the quotient rule. So again, pause the video, give yourself an attempt at all three parts here. We'll check in several minutes. All right, welcome back. This is our final example for part 1 of this lecture. So here we're going to have to use the quotient rule. Pretty straightforward. You should get simplifying your derivative here. 1 minus x squared in the numerator, and then x squared plus 1 squared in the denominator. Now here we have the possibility for the first derivative becoming undefined since we have a fraction, but if you try to do that, set that denominator equal to 0, since it's x squared plus 1, that has no solutions when it equals 0, at least no real solutions. So we can ignore the undefined possibility for a critical point and just now set the first derivative equal to 0. That basically amounts to setting the numerator equal to 0 if you were to clear fractions. And 1 minus x squared, you can solve that rather quickly, getting x equals positive 1 and negative 1 as your solutions. So that corresponds to 2 critical points. We have 2 critical points that splits the x-axis in 2 spots, giving us 3 intervals. The intervals being negative infinity to negative 1, negative 1 to positive 1, and positive 1 to positive infinity. We'll pick as our test points, going left to right, x equals negative 2, x equals 0, and x equals positive 2. And we're going to plug those into the simplified derivative, 1 minus x squared divided by x squared plus 1 squared. And again, we're not going to work too hard in getting the precise values, but we'll just determine the sign of numerator and denominator individually. The thought being a negative divided by a positive is negative, negative divided by a negative is positive, and similarly. All right, if you plug in your 3 test points to the first derivative, you should get as your signs in order negative first derivative on the leftmost interval, a positive first derivative on the middle interval, and then a negative first derivative on the rightmost interval. And we can make some conclusions from this. First, we can determine that our function is increasing on the interval negative 1 to 1, since the first derivative was positive there. Our function is also decreasing on the outer 2 intervals, negative infinity to negative 1, and 1 to infinity. Since we see a change in sign in the first derivative across each critical point, each critical point corresponds to a local max or min. Our critical point, negative 1, that sign change from negative to positive corresponds to a local minimum. And at x equals positive 1, that sign change in the first derivative going from positive to negative, that corresponds to a local maximum. All right, now definitely go back and review the examples we covered in creating the sign charts, since for the second and third parts of this lecture, we're going to be using similar sign charts to sketch graphs.